So we have discussed Butterworth filter. Now we are discussing Chebyshev filter. There are two types, type 1 and type 2. And in type 1, ripple is there in the pass band, and in type 2, ripple is there in the stop band. So that the transfer function of Chebyshev filter depends on the polynomial Cn, that is called Chebyshev polynomial. So Cn is a function which depends on the variable x, that is x is equal to ratio of the frequency and the passband frequency omega p. So omega by omega, it is a generally, you can say, normalized frequency by the specific passband frequency. So now we have seen some characteristics of Chebyshev polynomials. Cnx, you just have to go through all these properties. Okay, it is explained clearly and we discussed it. Now this graph we see that for type 1, where ripple is there in the pass band, okay, under that again two scenario occurs. One is when order of the filter is odd and order of the filter is even. So oscillation, you see that some at zero frequency there is a difference, that at omega is equal to 0 we get gain 1 for n odd, the order of the filter odd, whereas when n is even, the order of the filter, the transfer function or magnitude characteristics for omega is equal to 0 is 1 by root over 1 plus epsilon square. So it is the starting value from where it oscillates, the transfer function, the magnitude. So here you can see that how we calculate that what should be the magnitude. So let us say when n is odd, okay, so Cn is how much? Cn is equal to 0 at omega is equal to omega 0. Omega is equal to omega 0 means x is equal to 0, or formula for Cn is this one. Cnx is equal to cos s cos inverse n cos inverse x. So x is 0, that means cos inverse 0. Cos inverse 0 is how much? Cos inverse 0, it is pi by 2. Okay, pi by 2 is the angle. So cos of n pi by 2. If n is odd, that is 1 pi by 2, 2, 3 pi by 2, 5 pi by 2, that time it becomes, okay, so it becomes again 0. So 2 pi plus pi by 2, okay, or pi by 2, again it is 0. So at omega is equal to 0, the magnitude of the Chebyshev filter, you see the magnitude square function. So it is 1 by 1 plus epsilon square into Cn. So now this Cn is 0, so it is 1, or n is odd. Now when n is even, that time it is when x is 0 and n is even, that time it is how much? It is again pi by 2, but 2 pi by 2, 3 pi by 4 pi by 2, 6 pi by 2. So it is cos pi, nothing else. Cos pi or cos 3 pi, like that. So it is cos pi means -1. So Cn0 is -1. So if it is -1, then again coming back to this polynomial, it is -1 whole square, that means +1. So it is 1 by 1 plus epsilon square, or magnitude square, it is the function, so it is be root. So it is 1 by root over 1 plus epsilon square. Okay, it is explained here. So and passband gain is alpha p at passband frequency omega p. Passband gain alpha s at passband frequency omega s. Stop band gain is stop band frequency is omega s, and corresponding pass band gain is 1 by root over 1 plus epsilon square. Now at omega is equal to omega p, okay, at omega is equal to omega p, it is Cn1. Okay, so Cn1 means it is cos inverse 1 means 0. Okay, so cos 0, cos n into 0, it is cos 0, so it is 1. So it is 1 by 1 plus epsilon square at omega is equal to omega p at both the cases, okay, for n odd or n even, because n does not matter there because it is multiplied with 0. Okay. So it is 1 by root over 1 plus epsilon square. Now next we will see that what is the relation between some parameters. So you can see that at omega is equal to omega p, the gain magnitude function is 1 by root over 1 plus epsilon square into Cn. Cn is 1, so it is so. Now 20 log of it is what? It is 20 log of h omega. Okay, it is minus alpha p. Okay, so in maximum gain is 0 dB. So from 0 dB it goes below by alpha p, so it is minus alpha p. So now from there you can equate this alpha p with epsilon as we have done in case of Butterworth filter. So the relation is same, epsilon is equal to 10 to the power 0.1 alpha p root over. Then omega is equal to omega s at stop band. Okay. It is alpha s is 10 log 1 plus epsilon square Cn square omega is by omega p. Okay, because it is 20 log of this much, will give you alpha s, 20 log of hj omega at omega is equal to omega s. It is alpha s, so alpha s is now this one. Okay. So at omega now, so we can get the values of alpha s. Okay, it is 10 log of 1 plus epsilon square into putting the formula of Cn. So Cn is cos. So in pass band, in stop band, it was what? Cos hyperbolic inverse, that we told it is there, that for in stop band, that is x greater than 1, it follows hyperbolic function or decaying function. Okay. So we get this expression in place of Cn. This is the formula. Okay. Now in this equation, putting the value of for epsilon, we solve for n and rounding it to the next higher integer. So your formula becomes n. Here the term n is there. So from here, due to this, we get the cos hyperbolic term. So the order of the filter n is equal to this one, cos hyperbolic inverse of this factor by this cos hyperbolic function of these factors, numerator and denominator. And you see right side I have given one note that cos hyperbolic x inverse formula is ln x of x plus root over x square minus 1. Okay. So this is the that I have written there also. So now next part is the pole locations. Pole locations for Chebyshev filter. We have discussed for Butterworth filter for different orders n is equal to 1, 2, 3, 4. For different orders, we saw that the denominator changes. Okay, that means transfer function changes as order increases. So pole locations are dependent on the order of the filter. We have seen in the case of Butterworth filter. Now we are going to see for the case of Chebyshev filter type 1. Okay, because whatever the discussion is going on, it is on type 1 Chebyshev filter. Okay. So where the denominator is 1 plus epsilon square Cn square, okay, J Cn square, it was omega by omega p. So let us see again the formula that omega of Cn square omega by omega p, and in place of omega we write minus Js. Okay, because S is equal to j omega and omega is equal to S by j. So multiply both sides with j, numerator and denominator, we get j square divided by omega is equal to S by j. So denominator is j square and numerator is j. So minus js. So that is equal to 0. So from here you get Cn square minus js by omega p, that is equal to 1 minus 1 by epsilon square. Okay, so that is j square by epsilon square. Okay. So this Cn, okay, now this is both the square, so square can be cancelled out, and that means Cn of minus js by omega p is equal to plus minus j by epsilon. So what do we mean? That in place of Cn polynomial, Chebyshev polynomial, we write it as n cos inverse minus js by omega p, because we consider pass band. Okay, pass band formula is this, and because we want to know the pole locations, so pole means the frequency at which the gain is high. So we have to consider the formula for Chebyshev polynomial in form of pass band. So that is cos inverse n cos inverse js by omega p. If it would have if it is for stop band, then it would be cos hyperbolic, but it is cos for pass band. Okay. Then this is the formula for Cn. So cos of n cos inverse minus js by omega p, that is equal to plus minus j by e. Okay. So now let us say this cos inverse minus js by omega p. Okay, this is a complex term, so we write in term in term of some suitable variable, that is say phi minus j theta. Okay, phi minus j theta. Cos inverse minus j is by omega p. Let us say this is phi minus j theta. So plus minus j by omega, a plus minus j by epsilon, this equation actually now becomes cos of n phi minus j n theta. Okay, because it is cos of n into cos inverse of that term. So cos inverse we assume phi minus j theta, so it is multiplied with n. So now again cos, using the formula for cos a minus b, it is cos a cos b plus sin a sin b. Okay, so you have written there cos n phi plus cos j n theta plus sin n phi plus j n sin j n theta. So it is cos n phi cos h n theta. Cos j n theta means what? It is actually hyperbolic. What do you mean by hyperbolic function? Hyperbolic function is cos h theta is equal to e to the power minus theta plus e to the power theta by 2. But in case of cos theta, it is e to the power minus j theta plus e to the power j theta by 2. Okay. But cos hyperbolic theta means e to the power plus theta plus e to the power minus theta by 2. Okay. E to the power minus theta plus e to the power theta by 2. This is the cos hyperbolic function. So cos j theta is actually called cos hyperbolic theta. Okay. So similarly, sin j theta is actually j of sin hyperbolic theta. Okay. J of sin hyperbolic theta. So we are just putting the values over there. Okay. Now we'll see that equation 1. So we relate this with both left hand side and right hand side with real and imaginary part. Okay. So cos n phi plus cos h n theta is the real part, okay, that is 0. Okay. And imaginary part is sin n phi sin h n theta is equal to plus minus 1 by epsilon. Okay. So we get cos h n theta, that is not is equal to 0 because theta is real. Okay, theta is real, so it cannot be 0. So cos n phi, okay, part would be 0. Okay, cos n phi part is 0. So to satisfy this, n phi should be pi by 2, okay, or 3 pi by 2, etc. Or odd multiple of pi by 2. Okay, odd multiple of pi by 2. So n phi is equal to 2k minus 1 into pi by 2, or pi is equal to 2k minus 1 into pi by 2n. Okay. So this is the phase part, that is phi minus j theta. Okay. So now equation 3, putting this value of phi, we get, so just putting the values of phi we get there. So it is sine of phi, so it is 1. Okay, so sine this is the value of phi. Okay, so sine n phi is actually what it is. Phi is odd multiple of pi by 2, so sine pi by 2 means 1. Okay, so we get, or any multiple of pi by 2 for n, it is 1 or plus minus 1. So we that is 1. So we get h sine h of n theta. Okay, from this part, sine h of n theta is equal to 1 by epsilon plus minus 1 by epsilon. So from there we calculate n theta is equal to plus minus sine hyperbolic inverse 1 by epsilon. So theta is equal to plus minus 1 by n sine hyperbolic 1 by epsilon. So this is the two part of this term, cos inverse term. Okay. That means Chebyshev polynomial. So here we have cos phi minus j theta now is what theta and phi we have calculated. So it is what it is, the poles. Okay, so we have started with this discussion that cos Cn minus Js by omega p. Okay. So this is now equal to minus Js by omega p cos of minus Js by omega p. So here we get that cos of phi minus j theta. Okay, so if you calculate it, it will come minus Js by omega p. You have to go through this part. Then from there you see the variable s, okay, that defines you the pole's location, where phi and theta were given by those terms, those equation, okay, and you give the value of s. Okay, s depends on the s actually defines the pole locations, sk, that is j omega p into cos phi minus j theta. So now uh, here sk is this one, j omega p cos phi minus j theta. So in place of phi minus j theta, we are writing again the formula of cos a minus b. So this way you calculate, then you will get, it is a long calculations, but just showing the way how it is done to calculate the poles. So just go through these steps, okay? Then you will see that there are terms sin h theta and cos h theta. So you will be having this term mu, okay, that is mu epsilon inverse plus root over 1 plus epsilon to the power minus 2. So here just putting all these values, it is a long calculations. So you will see that pole locations are given by coming on a circle, okay, a cos phi k plus jb sin phi k, which sigma k and plus j omega k. Okay, so no need to remember these all steps now. Now you see that some general method. Okay, then it will be clear. Now from this you will see that this is important. The poles can be determined. So just I am underlining this. Just I am underlining this. So the poles can be determined using, so your variable s or pole is sk is equal to a cos phi k plus jb sin phi k. So where a and b are given by this term. A is dependent on passband frequency omega p and b is dependent on stop band frequency omega p, and this is multiplied with another term is related to mu. Mu is epsilon inverse plus root over 1 plus epsilon to the power minus 2, and this is, there is phi k. So phi k formula is this one, pi by 2 plus 2k minus 1 divided by 2n into pi. Okay. So this way, if you use all this frequency specification omega p, okay, and epsilon, okay, then you will be able to design the Chebyshev filter. So now you see some characteristics that the poles of the Chebyshev transfer function are located on an ellipse in the S-plane as shown. So the equation for ellipse is given by sigma k by a square plus omega k divided by b square. So where this is sigma k is equal to a cos phi k, okay, and so these are the poles locations where A and B are the minor and major axis of the ellipse. Okay. So this is the poles for n odd. So just showing this some characteristics. Now then we go to Chebyshev type 2 filter. Okay. So for Chebyshev type 2 filter, here you see at denominator uh, of the transfer function, some this Cn, there is now two polynomials comes, okay, that represents both pole and zeros. Okay, so here some zero is included, zero to represent some gain in the stop band. So zeros are there where at some specific frequency the gain would be zero. Okay, here you see these ripples are there. So in the ripples, this is zero, the gain is zero at some frequencies. So those are defined by this extra term, Cn square omega s by omega. Okay. So here directly we are writing the formula. It is very critical calculations that where should be the poles and zeros. So it has both poles and zeros. Okay, and this formula is given by this for Chebyshev type 2 filter, and zeros are located on the imaginary axis at the point j is sk is equal to j into omega s divided by sine phi k. Okay. So and the poles are located at the points xk and yk given by this formula, and with sigma k and omega k, mu, and finally the order of the filter is given by this. Okay. So you have to remember all these equations and how these are coming. It is out of scope now. Okay. So now there is some comparison of Butterworth and Chebyshev filter. Okay. Here we can see that magnitude response of Butterworth filter decreases monotonically as frequency increases, whereas for Chebyshev filter it exhibits ripples in the passband or stop band according to the type. So Butterworth in Butterworth the gain filter magnitude response decreases monotonically as frequency increases. There some ripples behavior is there in the Chebyshev filter, and in transition band is more in Butterworth filter when compared to Chebyshev filter. Transition band is more in case of Butterworth filter when compared to Chebyshev filter. The poles of Butterworth filter lies on a circle, okay, that we have seen earlier, S1, S2, S3, S4, S5, S6. The poles are lying on a circle, whereas the poles of the Chebyshev filter lies on an ellipse. Okay. Now for the same specifications, the number of poles in Butterworth filter is more than that of Chebyshev filter. That is, order of the Chebyshev filter is less than that of Butterworth filter. This is a great advantage because less number of discrete components will be necessary to construct the filter. Okay. So you know that if order of the any filter or structure decreases, okay, then increases, then complexity or design cost or need of components will be increased. More number of components will be required. The delay element, then gain any element will be more. But if you get the same results, if you get the same result, same response with lower order system, lower order filter, then why not you choose that? So that's why Chebyshev is advantageous than Butterworth filter. Okay. Now there are some steps to design analog Chebyshev filters. Okay. So first step is we'll see this one example, then it will be clear and very easy. Okay. So one problem is given that design a Chebyshev filter that is type 1 with a maximum passband attenuation of 2.5 dB at omega p is equal to 20 radian per second and the stop band attenuation of 30 dB at omega s 50 radian per second. So these are the filter specification. Also you have seen today in the lab session, okay, that how to specify the frequencies and attenuation terms. That is omega p is 20 radian per second, omega s is 50 radian per second, and alpha p and alpha s is 2.5 and 30 dB. So now putting this over the formula of cos hyperbolic inverse lambda by epsilon, cos hyperbolic inverse 1 by k, okay, where lambda is given by this and epsilon is given by this, we are getting 31.6 and 0.882 lambda and epsilon correspondingly, and k is this 0.4. So putting this over the formula, we get n is equal to 3. Okay, that is n is equal to 2.726, and rounding to the next integer. So it is next higher order integer, it is n is equal to 3. So first step is over. Okay. Then what is the next step? Is calculate A and B. Okay. What is A and B? A and B are omega p into this formula, and B. A and B are given by this formula. It depends on omega p and mu. So you have to calculate mu. So mu is in epsilon inverse plus root over 1 plus epsilon to the power minus 2. So from there we get the values of mu AB, and then use the poles SK formula for poles. SK is equal to A cos phi k plus JB sin phi k. So where phi k is this, there are k is 1, 2, 3, order up to 1, 2, 3. So calculate these three angles, 120 degree, 180 degree, 240 degree. Okay. So now putting over these three values, we get S1, S2, S3. Okay. So that means denominator is, okay, again multiply S minus S1, S minus S2 and S minus S3. He will get this form value, S plus 6.6 into this. And numerator is how much? It is numerator is matters because it is 1 by 1 plus epsilon square. Okay, so if you use that value, okay, so since it is a type 1 system, for type 1 it is what is the value for omega is equal to 0? It is 10 is odd, so so at omega is equal to 0, you have to calculate the gain. Okay, so here you put value omega is equal to 0 in this equation. Okay, omega is equal to 0, so let me write over there, because this is the maximum gain. Okay, so you just mention it here, that insert symbol. That is gain at 0 frequency. That is maximum gain. So maximum gain is calculated as this way. In this formula, in the denominator, okay, you will get, putting omega is equal to 0 or s is equal to 0 in the denominator, we that is gain, that is unity gain. To obtain unity gain, so when to obtain unity gain or gain at 0 frequency, okay, that is maximum gain. So you have to keep the same value in the numerator, so that this, when frequency omega is equal to 0 comes, both numerator and denominator cancels, so that numerator and denominator cancels. So is it clear?
Yes, sir.
Okay. So now this is a long steps, but you have to remember some formula to design those kind of filters, okay, Butterworth and Chebyshev. So you have to design the denominator and numerator. Okay. So when omega, so this way the filter is designed, but it is just to create calculating the analog transfer function, not it is in the digital form. So for digital, you have to convert it into some suitable relation between S and Z. That will be discussed later in the next module. Okay, but after this, those two topics are remaining. One is elliptic filter and the frequency transformation or filter transformation, that is low pass to high pass to low pass. So direct formulas are there. So I will discuss, okay, later when you will get the scope of this. That means when you will again meet, okay, that is in the next week after the vacation. Okay. So students, you have quiz today from 7 p.m. Okay, so do you remember? Do you know, or I think it was informed that quiz is on 7. It is confirmed from 7 o'clock today evening. So we will be prepared. Okay, and anything to discuss today now, because we will meet again after the vacation, that is on Monday.
No, sir.
Okay.
Sir, this slide which you are teaching us is uploaded on the team, sir. We will refer that.
Okay. 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 Thank you then.
Thank you, sir.
Hmm. Now you may leave.